This is a continuation of the last video of the class notes. So let's do some practice here. Notice we're looking at vapor pressure versus temperature in this case. And what is the normal boiling point of each liquid? So when you see the word normal boiling point, that's the same as standard pressure. So in this case we have 101.3 kilopascal. You could also have 1 atmosphere or 760 millimeters of mercury. So at this pressure, where does it intersect each line? So you can see chloroform intersects at 60 degrees. So that's the normal boiling point of chloroform. Ethanol intersects at 78 degrees. Ethanol is an alcohol, that's about right. Water intersects the line here, you can see, at 100 degrees. That's the normal boiling point of water. Ethanoic acid intersects just past the 120 degree mark, about 125 degrees at the standard pressure. Let's try another one. What pressure is necessary to get each liquid to boil at 60 degrees? So you'll look at 60 degrees down here, temperature, and now you go up to each individual line. So you can see for ethanoic acid, about 16 kilopascal. For water, it's about 23 kilopascal, just above 20. For ethanol, 60 degrees, go up to ethanol, come across. We're looking at about 50 kilopascal. And finally for chloroform, go all the way up to the top. And you're at about 101 kilopascal. Which liquid is least likely to boil under the given conditions? So if you look at all these, chloroform will boil quite quickly compared to the rest. And you look at ethanoic acid, it's way to the right. It takes quite a lot of temperature to get it to boil because it has a low vapor pressure. Its tendency to boil is very low. Which one's most likely to boil? As we said, it'd be chloroform because chloroform has a high vapor pressure or a high tendency to boil. So let's look at 80 kilopascal over here. If you go over to the lines, chloroform needs about 55 degrees to boil. Ethanol needs about 70 degrees. Water would need about 90 degrees. And ethanoic acid would need about 110 degrees, so much more temperature, which shows again low vapor pressure here, chloroform, high vapor pressure. The last thing we want to look at is phase diagrams. These represent the relationships among solid, liquid, and vapor or gas of substances in a sealed container. Again, you have to have a closed container. The conditions of pressure, that's on the dependent variable y-axis, and temperature is the independent variable on the x-axis, at which two phases exist in equilibrium. And they're indicated on the phase diagram by a line separating the phases. So look between solid and liquid. You see this line right here? That's when you go from solid to liquid, that would be melting point. If you go from liquid to solid, that would be the freezing point. Then the liquid to vapor line is a curve. Liquid to vapor is boiling. Vapor to liquid is condensation. Solid to vapor down here, solid to vapor would be sublimation. Vapor to solid would be deposition. So each slope line represents the equilibrium conditions for one of the phase changes. So let's take a look at the melting point, freezing point. You can see it's the blue line here. And again, depending which way you're going, it's melting or freezing. How about the boiling point, condensation point? That's the green line. Boiling to the right, condensation to the left. And lastly, sublimation and deposition points are down here. And those are the phase changes. Now, we can put all three together, and we call it the triple point. There is a point at which all three phases, solid, liquid, and gas, can exist exactly the same time, but it takes a very particular pressure and a very particular temperature. And you can see for water 0.016 degrees Celsius and 0.6 kilopascal. So very low pressure, very low temperature. And here's a picture of it. The flask is at the triple point. There's freezing, melting, boiling, condensation, sublimation, and deposition all occurring at the same time. Let's do a little practice. Let's look at this question up here. What does normal mean in terms of melting point, boiling point? Give all the units. We've talked about that. And on this graph, you can see it's over here 101.3 kilopascal. But it can also be 1 atmosphere or 760 millimeters of mercury. That's what we call standard or normal pressure. What phase would exist at 50 kilopascal and negative 10 degrees Celsius? So if you go up to the graph, this is 101, so 50 is right around here. Okay, negative 10 degrees would be behind 0, so we're talking up in this area. So that's a solid. Solid would be in here. Which phase would exist at standard pressure? That's along the 101.3 kilopascal line and 50 degrees. Here's 50 degrees, so right up here you can see it's the liquid. Lastly, what phase exists at 10 kilopascal? That's probably right around here. And 80 degrees. 80 degrees here, so you're looking in the vapor phase. So you see how to work the graph. When we consider water, we need to understand that water is unique. Follow this solid line here, the solid liquid phase change line. If you go up that line, pressure is increasing. You also notice it goes to the left, so the temperature decreases. And what happens is water is a unique compound that actually expands as it freezes. Every other substance contracts as it freezes. All other substances in creation, the solids contract as they freeze, meaning that the solid liquid line would actually slope to the right. God's pretty cool, isn't he? So one final review. What are the postulates of the kinetic theory? All matter is composed of small particles. These particles are in random, constant motion, and there are collisions between particles that are perfectly elastic. When does this theory break down? At extreme temperatures and pressure, basically. Very low temperatures, the gases will expand less for a given pressure change than they do at very high temperatures.